Okay, we're going to have a look at some simple second order differential equations. So by second order we mean they've got a second derivative in them. And the only type we're going to worry about are ones where we can write them in this form. So basically something times the second derivative plus a constant times the first derivative plus a constant times the variable equals, at this stage we'll start with 0, and we may get onto a stage where we can deal with something slightly different from 0. Down here, some function of x. But the guts to all of these things is that you set up what's called the auxiliary equation. So you just replace the derivatives of y with m, and you end up with this equation here. So it's just basically a quadratic in m, and you solve the quadratic, and depending on how the quadratic solves, so all this bold stuff here is just going to be on your formula sheet. So you get exactly the stuff on the formula sheet, and depending on how the quadratic solves, you just pick the appropriate one of these, and this is your general solution to the equation. So just a matter of picking it off the list, really. So by far and away the best way to have a go at explaining this is to do an example. So I'm going to do a few examples of this. So here's the first one, conveniently labelled example 1. So here's our differential equation. So it's 1 times y dash minus 7 lots of y plus 12y equals 0. So the auxiliary equation is just going to be 1 y squared minus 7y plus 12 equals 0. Okay, so that's what we mean by the auxiliary equation, and that's completely wrong because I've used y's and I should have been using m's. So it's 1 lot of m squared minus 7m. We use m for the auxiliary equation, and basically you've got to solve that, and this one factorises quite nicely. This factorises to m minus 3 m minus 4 equals 0. So it has solutions of m equals 3 or m equals 4. So we're dealing with a situation where we have two real and different solutions to the auxiliary equation. So the type here is they're real and different roots. So our general solution is going to be of this form here. Okay, so y equals a lots of e to the first solution times x plus b times e to the second solution times x. So in this case, the general solution is y equals a e to the 3x plus b e to the 4x. And it doesn't really matter which ones the 3 and the 4 go, because when you work out values of a and b, it'll come out with the right one. A general solution, and for the particular solution we're trying to find out, we've got this initial condition when x equals 0, y equals 3. So at x equals 0, y equals 3. So we have the case that 3 equals, if x is equal to 0, both of these things will go to 1, so 3 is a plus b. And the second condition we're given, because we've now got two variables, we need two conditions to work them out. So the second condition is that the derivative of y equals 11 when a equals 0. So we have to differentiate this thing. So y dash is 3a to the 3x plus 4b e to the 4x. And again, at the point where x equals 0, we know that y dash equals 11, and that's going to be 3a plus 4b. So we have a simple set of simultaneous equations to solve. So you can go about doing that any way you like. I bet it's 1 and 2. Yeah, b's 2 and a's 1. So solving those simultaneous equations, b equals 2 and a equals 1. You can do it any way you like. So the particular solution is y equals a e 3x plus b e to the 4x. Okay, so that's the particular solution for this differential equation with these two initial conditions.